Dr. Mullens is at the University of Oklahoma School of Meteorology. Her research focuses in the area of characterization of synoptic and thermodynamic evolution of multi-phase winter storms. The title of her presentation is Weather and Climate Impacts to Transportation in SPTC Region 6. Dr. Mullens.
Which one is my, is this the laser pointing device? Hey, good afternoon, everybody. This presentation is changing tack just a little bit. I am not an engineer. I am a meteorologist by training. In the lead up to this presentation, I consulted my dad, who is a civil engineer, about how concrete works. And if I've learned anything this morning, I have learned that it is not an easy question to answer. So this presentation is looking more at the meteorological and climatological aspects of our region. Clearly, our two disciplines have some things in common, and one of which is that weather and climate tremendously impacts the movement and safety of transportation and also infrastructure. So in the past 60 years or so, 4 of the 5 member states of the Southern Plains Transportation Center were in the top 10 for the number of FEMA-declared disasters. That's the table on the left-hand side. You can see that Texas and Oklahoma average over 1 a year over that period. A recent assessment by the Southern Climate Impacts Planning Program, SCIP, assessed various sectors in Oklahoma, so agriculture, transportation, utilities, and basically asked them what were the weather and climate impacts that they were most concerned about. And as you can see in the table, on the figure on the right-hand side, that really the top 9 or 10 of these relate to the extremes in our environment, not necessarily the average temperatures or average precipitation. For this presentation, I'll just be concentrating on a few of these that our region is particularly vulnerable to, including heavy rains and flood, winter storms, and tornadoes. So I'm sure many of you, especially those who deal operationally with the impact of weather, these statistics are not going to be all that surprising. Obviously, crashes, there are a number of reasons for crashes and incidents on the road. About 23% of those are due to weather conditions. The figure on the bottom left just shows a tally for Oklahoma. The majority of crashes are when the roads are wet, with a significant minority after that being snow and fog. I'm sure all of us, one degree or another, have experienced adverse weather during peak travel periods, and that can be extremely difficult. Infrastructure-wise, our extremes of temperature lead to thermal stress on pavement, resulting in fatigue. I'm sure many of you know much more about that than me. Extreme heat and to an extent extreme cold temperatures impact maintenance scheduling. So when you have your staff going to fix a portion of your infrastructure, you can't really do that if the temperatures are too hot or too cold. Aviation, actually, we know it more for getting disrupted during winter systems, but in the summertime when we have extreme heat waves, there are issues with weight loading on aircraft and takeoff times and things like that. So if you arrive somewhere and your luggage doesn't and there was a heat wave, it may be just due to issues with weighting of the aircraft. Softening asphalt, railway lines have extreme trouble with heat and also increasingly issues with the bridges, especially as they are aging, with the temperature issues compounding that. And also flooding and debris, especially in the cities, overwhelming drainage systems. And although it doesn't happen often, there can be extreme damage to road and rail networks. And during the winter, de-icing treatments are problematic for pavement. Economic-wise, adverse weather results in numerous local regional delays, changing traffic speeds, changing volume of traffic, obstructions. And about 23% of non-recurrent delays nationally due to winter weather in particular, and traffic times can increase by up to a quarter in peak periods during precipitation. Trucking companies in particular have trouble because they're on the road all the time, and they lose a lot of money when the weather is particularly extreme. This last winter was one of those unusually cool winters, and so winter road maintenance already costs a lot. 3/4 of states found themselves over budget because of the conditions this past winter. So moving on to our first of our regional risk factors, heavy precipitation and flooding. Flooding is actually the #1 US disaster. We think of it as being things like tornadoes, but flooding kills more people on average than any other extreme weather event. Most flooding deaths are due to people attempting to drive through high water without really understanding the problems that can entail for their vehicle. So meteorologically wise, one of the biggest factors, especially here in Oklahoma, is convective precipitation of thunderstorms. We typically get most of our flooding events in the spring and early summer. When we have thunderstorms that repeatedly move over the same area, we can get a lot of precipitation in a short amount of time. Deep atmospheric moisture content, something called precipitable water, is very important, and the higher that is, the greater the likelihood of some sort of heavy rainfall event. And other meteorological variables we look for, including large-scale lifting of the atmosphere, which allows for these thunderstorms to form. And also near the Gulf Coast, so in our member state, Louisiana, tropical cyclones are a big issue. So just maybe to refresh your memory of a few events, those of you that are sort of operational with the DOT and that, or with the city may remember some of these. In the past 4 years, there's a particular part of Oklahoma City that has flooded 3 times. There's also been widespread flooding on 2 occasions in the last 4 years. This first one here is June 14, 2010, about 7 to 8 inches in the city of Oklahoma City, widespread flooding. The second one was May 31st of last year. I don't know whether anybody recalls that event. That was quite an interesting one just because of what had happened the week before, a major tornado outbreak in Moore. And in this particular situation, we also had a tornado in El Reno moving towards the city. But the real killer that day was, in fact, the flooding, because that was an extremely slow-moving thunderstorm with a lot of precipitation, and that also produced about an exceedance of a 1 in 500 year event for the city. And there were fatalities associated with that, as people were taking shelter from the tornado threat, but did not perceive the issue with flooding, and ended up in culverts and ditches and things like that. And that picture just shows, does anyone know what highway that is? Because I tried to find out, but it was Eastern Oklahoma County after that particular event. And then the final event was not a 1 in 500 year. It was probably closer to 1 in 100 or less, about 2 to 3 inches of accumulation, but that also led to localized flooding in the city. So 2 1 in 500 year events in 4 years. So obviously our region experiences variable precipitation. This is a chart that shows annual average precipitation in Oklahoma since 1895. And as you can see where the brown is, that's just a deficit in precipitation for a year, and the green is more precipitation than usual. And we're bouncing up and down throughout this time. The 1980s and 1990s were known for, across the nation actually, more precipitation than normal. But in general, there is high variability. And also precipitation extremes are not necessarily correlated to annual averages. So you can still have a very heavy rainfall event in a year that has lower than normal total precipitation. Here is a plot showing the 99.8th percentile. So only 0.2 events get greater than this. And this data is actually, there's a grid point every about 30 kilometers. So it only measures once every 30 kilometers. So this may even be a little bit conservative. But the greens indicate about 3 or so inches, the blues more like 4 to 5. And this follows the track of the annual precipitation. Generally speaking, in New Mexico would not be experiencing the kind of precipitation extremes that you can get in Louisiana. And over these 6 decades, there's been generally up and down variability depending on where these very heavy precipitation events set up. But if we look a little more at perhaps some of these trends, and we look at the contribution of 3 inches or greater precipitation to the total number of days per decade, you can see that those light up generally in the Gulf Coast region. So this is a measure of how extreme is each individual precipitation event. And you can see that the 1978 to 87 period is on the mid right, and the bottom right, 1998 to 07, were 2 periods of time where there was a reasonable amount of heavy precipitation. So if we take a threshold, let's say 0.8% contribution of those types of days per decade, and we look at how that has changed in time over those 6 decades, the latter 3 decades, and part of this is to do with the fact that the first 3 decades were drier than the latter 3 decades. There is some relationship there, but the latter 3 decades have about a 39% increase in the number of these grid points, these 30-kilometer spaced areas with these extra heavy precipitation events. And if we look at an even higher threshold, say 1.5%, we clearly see that the last decade stands out in that regard. So the National Severe Storms Lab is currently in the process of improving flash flood forecasting, which should be of use if you're a planner and you're looking out in advance and trying to figure out what your potential impact is going to be, what roads you might need to be monitoring. This aptly named FLASH system uses multiple sensors, so rainfall radar and rain gauge. It uses that data and it forces a hydrological model. It also uses information about the atmosphere to produce flash flood forecasts about 6 hours in advance. You can generate this wherever there's radar information, so our National Weather Service radar that we have. And this forecast here that I'm showing you was based on that May 31, 2013 last year. And the brighter colors there, it doesn't come up very well, I know, but the brighter colors show the areas which are experiencing very heavy rainfall. And here, I think maximum was about 1 in 200 years. So the actual event itself was even more problematic than that, but this would still provide pretty good guidance with a good lead time. And this is not an operational product as yet, but it is being tested in order to be released as such. And moving on to winter storms, there's the obligatory slide with Atlanta. I'm sure many of you are familiar with what happened there, but now, obviously the vulnerability of a region is partly to do with how much experience they have of a type of weather system. In our case here in Oklahoma, we experience several winter storms a year, so it's enough that we're known for it, but it's not enough that we're completely adapted to it. So our snow melts afterwards, our ice melts, and then we go through it all again maybe a month or 2 down the road. So there's a reasonable amount of preparedness here. In Atlanta's case, there were various reasons for what happened here, but one of which I found out yesterday from a National Weather Association conference is that the climatology events in that region shows that they're extremely rare. There's only 2 events in the past over 100 years where there was 30 degree Fahrenheit or less temperatures, measurable snowfall, and it was a work day. So, Atlanta has some form of excuse. If people aren't familiar, winter storms have a multitude of phases associated with them. And part of that's to do with how far this warm air can go over the cold air at the surface. So with snowfall, that's a completely freezing profile in the lower atmosphere. But with sleet and freezing rain, we have some sort of warm air that's moving over this air that's below freezing at the surface. And especially for freezing rain, the deeper that warm air is, the more likelihood we're going to have ice towards the surface. But it's balanced by the fact that in some ice storm events we've had here in Oklahoma, we've had very warm days, and then all of a sudden we have an ice storm, and our roads don't get below freezing. So that's a good mitigating factor for some of our problems. But of course, the electrical utilities still have problems, which feedbacks to issues with the movement of transportation in certain areas. Just to compound the importance of the ice events for the region, this research shows on the left-hand side, you see the proportion of ice storm reports that were also associated with a federal disaster declaration. On the left for ice and on the right for snow. And what that shows there is that in most areas, at least half to 2/3 of those ice events were associated with a federal disaster declaration, whereas in the case of snow, it's more like 1/3 to about 40%, which illustrates the issues that we have with ice in this region. And just to briefly go over last year, this is generated by a private company called Risk Pulse. They just showed the tracks of various different winter storms and some very rough impacts, including problems with freight movement. About 25,000, 50,000 trucks a day were displaced or couldn't move, and particularly in our area, which is the green shaded, or I guess it looks more blue actually, just issues again with the snow, wind, and ice. And very, very broad swaths of the country impacted at one time, which again poses significant problems for the movement. For our specific location, Oklahoma City, this is just a trend in ice versus snow events over the past 40 years. And what's quite interesting here, the red is snow, the green is ice bar plots, but then we also have 5-year moving averages. And you can see a general decrease in the amount of snow, but the ice has generally remained rather steady. On the inset figure, there is 30 years worth of liquid water equivalent, which is the amount of precipitation in the phase of ice. And you can see that the 20 years between 1980 and 2000, despite having about the same amount of ice events as the last 10 years, did not have as much precipitation. So there's some sort of potential change in the character of our events, at least over the past 30 years, which we appear to be getting a little bit less snow and a little bit the same ice, so therefore it seems like we're getting more ice, but we're not really. And of course, freeze-thaw cycles. One of the aims of my research actually is to develop very high resolution measurements for freeze-thaw and its variability across the entire region. And we have a data set that goes to 1 kilometer resolution for 65 years. This is not that data set. This is actually a slightly lower resolution. And what it shows here on the left, you have freeze-thaw cycles, so it just shows you the average freeze-thaw, and many of you are probably familiar with the distribution of freeze-thaw over the region. The middle panel shows the variability in the maximum temperatures associated with freeze-thaw. So obviously, the more variability in your temperature, the potentially more damage to your infrastructure. And this is more so in the case of the maximum temperature than the minimum temperature, especially over the southern high plains, where there's probably not as much cloud cover, and so you can get much more variable temperatures there. So forthcoming is a very high resolution analysis of this. And then tornadoes. We probably know a lot about tornadoes from living here. We are in one of the peak regions for tornado activity. Not so much for actual thunderstorms, but the thunderstorms that can produce tornadoes are more common in this area. The climatology, the distribution by month on the bottom right shows that tornadoes are at their maximum April through June, and during the day, unfortunately not so good for evening rush hour, they tend to maximize in the early evening. So trends in tornadoes are difficult to really look at because tornado data is based on reporting, and so now we have 1 billion people on the road every time there's a tornado outbreak who can call in, and we know exactly where the tornado is. But back in the day, that was not so much the case. However, researchers at the National Severe Storms Lab have ascertained that there's one type of tornado that has not got this reporting bias in quite the same way, and that's the F1 tornado, which is the fairly sort of mild but still damaging tornado. And so recently there's been some evidence to suggest that the peak in our tornado season, so it's in May, has shifted a little bit towards April, so about 10 days earlier. And Harold Brooks at the National Severe Storms Lab has shown that there has been a little bit of a change in the character of our tornado days to favor more tornadoes on a single day. So these figures just show the F1 tornado, the count on the left-hand side. And on the right-hand side, you see the number of tornado days. The number of tornado days has dropped, but the count of tornadoes has remained the same, and that's for F1 tornadoes. So again, if we look at sort of kind of the current state of the art, which could be of relevance to those of you that do deal operationally with severe weather emergencies and how you're going to reroute things and what kind of preparedness you want to have, researchers are working on something called warn-on forecast. So traditionally, we've warned when a storm has developed characteristics that lead us to believe there's a tornado, you get a tornado warning. And that's a polygon-shaped warning area that encompasses maybe the whole of Oklahoma City or something like that. So that's helpful, obviously, but there's a high false alarm rate. So the tornado itself is maybe 1 kilometer wide at most, and then you've got this big area that you're warning. So with the improvement in computer power, there's now the ability to actually model these types of storms before they've attained those tornado characteristics, to model them ahead of time up to about an hour, and therefore provide a warning on a forecast, not on an observation. So what that would do is that you would run a lot of these different models to account for the uncertainty in them. You run them ahead about an hour after your storm has begun to develop. And then based on where the track of that system is, you can develop probabilistic guidance to that. So this figure here just shows the dark red is bad, the lighter colors are not so bad, and based on a probability from 0 to 1, how likely is your individual location going to get hit? And that would be updated as more real-time information becomes available. So what this allows you to do is specify a certain threshold of risk that you're willing to take, let's say 20%. And then once it looks like you're going to be exceeding that, then you begin to establish your plans. And that's actually a paradigm that's coming into play, hopefully in the next few years or so, for how these systems are warned. And not just for tornadoes, but also for things like winter storms. What's the likely path of the ice? What's the likely path of the snow? And other types of severe weather. So that's some of our weather issues. Now let's deal with the climate issues. So climate is defined as weather averaged over some period of time. So if we want to know what the climatological mean temperature is on January 1st, we would look at the temperatures averaged over some 30-year or even longer period to ascertain that. Climate variability includes natural processes that change our average conditions over seasons to years to decades. So one of those factors is, for example, El Nino. And we know that El Nino has some effects on North American weather and climate conditions over a period of seasons, maybe years. There's something else in the high latitudes of the northern hemisphere, the Arctic oscillation, or some people call it the polar vortex. You know, when things like that happen, we have some longer term changes that oscillate year to year. So this figure here is just global average temperature. And you can see that there are years that are warmer, there are years that are colder, it kind of just bounces around. Then we have climate change. And climate change is when that system is not behaving as a stationary system. So a stationary system would be one where we would just keep having these up and down cycles, and that would be what it would be out to the future. And a lot of our planning horizons basically factor for a stable climate system, one that doesn't have any particular trend one way or the other. A lot of our infrastructure is designed for 50, 70 years maybe, and how we design it, we base it on a lot of the present conditions and consider those to be unchanging. However, globally, some of these conditions have been changing, which weight the dice in one direction or another a little bit. So understanding these conditions, particularly in the extremes, like what we have talked about, are important in the long-term planning, especially for the infrastructure when you have you're planning for a long lifetime of your bridge or of your road. And the transportation community has got on board with this, and there have been some needs. So the community has asked for more information from meteorologists and climate folk, and risk assessments, building kind of long-term planning visions for how this information can be incorporated as you move ahead. So some of these groups are the Transportation Research Board, the American Association of State Highway and Transportation Officials, and some of the other federal and state guys. So some general projections. These are from the National Climate Change Assessment. This is a large group of researchers, and they analyze the latest information, and they do that about every sort of 4 or 5 years or so. The increase in the number of consecutive dry days is fairly robust signal through the Great Plains in the southwest. So it just indicates the number of days where there's no rainfall. The length of those days could potentially be increasing. And this considers a maximum worst case scenario, which is assuming that we just carry on in our same pattern and our same sort of extrapolate forward, increasing greenhouse gas emissions as we continue to grow society. There's also a risk of heavier precipitation events. So even though we might be drier, we might have more of these extremes. And I don't know too much about slope stability, but I know that could be an issue when you have changing character precipitation like that. On the left-hand side, this is a fairly vague plot, unfortunately, but it just indicates there's about 2 to 3 times increase in the number of 1 in 20-year precipitation forecast by this large group of climate models. And then for Oklahoma and Texas on the right, this is a higher resolution information, changing the number of days of the top 2% of precipitation. So one day may not seem like months, but that is the top 2% of precipitation. And then this is perhaps more robust than any other is the increased probability of summer heat waves. And I know there was a gentleman with a poster who's dealing with temperatures on bridges, and this could potentially be a factor moving forward. The panel on the left-hand side shows the hottest 2% temperatures from historical climatology. So they take the historical information from 1971 to 2000. They know what their hottest days are based on that, and then they see how those have changed when you look forward to 2041 to 2070 with this group of climate models. You can see that for Oklahoma and Texas, and I'm sorry if folks from New Mexico, that has changed a little bit, as has the number of days with temperatures above 95 in Arkansas and Louisiana, which is about a 50% increase over that historical period. So I am part of the South Central Climate Science Center, and that's based in Norman. And that has partnered with the Southern Plains Transportation Center for the recent Climate Transportation Summit, and hopefully for future endeavors. The Climate Science Center's mission is to provide decision makers such as yourselves with the science tools and information they need to address the impacts of climate variability and change on their areas of responsibility. And one of the ways on our end that this is working is to evaluate those climate models to make sure that they are realistic with respect to what has happened in the past, with the kinds of trends we see in the past, that they're doing what's physically appropriate, they're actually acting like the atmosphere would, and also evaluating some of the products that come from those, including high resolution information that is generated from these global models. And so I'll be working in the winter season, which is a little bit less understood, focusing on the freeze-thaw cycles and the trends in temperature and precipitation, and also looking a bit into our winter weather and how that has historically varied and how it might vary in the future, to develop some high-quality climatological information that can be used in risk assessment. Then we do want to focus on extremes of temperature and precipitation since they impact a large sector, and use the best available observational and model data. And importantly, one of the things we'd like to do is collaborate with transportation professionals. So I don't know how relevant some of this is to your particular areas of research, but if you are planning on incorporating weather or climate information, or your agency is interested in longer-term planning and risk assessments, we'd be very happy to help provide the information to make the best, to do the best with that. So if you're interested in that, please do contact me further, either after this or at the email address. Okay, thank you very much. I could ask a further question. What data do you think would be most relevant to your situation?
Well, I mean, I'm not a civil engineer, but my thought is, since it's dry, wet, moisture affect that pavement, maybe the design, maybe then we could have that incorporated in.
Yeah, so things like precipitation extremes or soil moisture or something like that. Yeah.
And somehow convey it to the truckers or whatever agencies that need to be adjusting these type of.
Yeah, I mean, I think for long-term planning, it'd be really good. There is obviously now there's a lot of great things that the transportation community has done. Intelligent transportation systems that now use real-time information to help truckers and other folks avoid ice or problematic. But certainly, I mean, what I'm interested in is if any of you have a sort of a longer-term study that you want to conduct.